In this lesson, we're looking at integral notation and rational numbers, with a little bit of a look at the real number system, and we'll also be looking at mostly converting terminating and recurring decimals into fractional form, and vice versa. So we'll start with the real number system. This is something you should be relatively familiar with. So if we start by looking at all numbers and noting that it breaks into two sides, we've got real number system, represented by that set, real numbers, and complex number system, represented by this symbol. Now, complex numbers is something we'll go into at a later date. I'm not going to talk about it at all really now. We'll just say that it includes imaginary numbers, which is I and the square root of -1. Okay, our focus is the real number system, and the real number system can be broken down into rational and irrational numbers. So rational, and the set is Q, and irrational, and the set is I. Rational is our focus today. Irrational will break down really quickly into surds, and an example of that might be square root of 5. A square root or a fractional index where we cannot simplify it down to an integer value, and transcendental numbers, which are irrational constants, and one of them you'll know quite well, which is pi, and there's also Euler's number, and a whole slew of different transcendental numbers that you can look up in your own time. With rational numbers, we can break them down into decimal and fractions. Reality is that rational numbers are numbers that can be put in the form A on B. So all the decimal forms that we're looking at here are decimals that can be converted into fractions. So basically we're looking at terminating decimal, and that is something along the lines of, let's say, 1.35. So it's only got a finite number of decimal places, and also reoccurring decimal. And reoccurring obviously has infinite decimal places based on some reoccurring pattern. So for example, we might say 1.12 reoccurring or 1.3 reoccurring. Now, a big chunk of our lesson today is that we're going to look at these decimal forms terminating and reoccurring, being able to convert them into fractions in that form A on B, and vice versa, being able to go from fractions and turn them into either terminating or reoccurring decimals. Okay, so hopefully you can see that system. Our focus is rational. At some point we'll look at surds and we'll examine irrational numbers, and complex numbers will pop up in Unit 2 of Specialist. So if we had to break this down and look at rational and irrational numbers, rational can be represented in fractional form. So represented as A on B. If we can't represent it in a simplified fraction form where A and B are integers, then it's not rational. Irrational cannot be represented in the form A on B for all values A and B, which are a set of integers. Basically, the idea with irrational is you've got no reoccurring pattern in the decimal places. There's no pattern that you can determine to be able to convert it into a rational form. Okay, so what we'll look at first is a process of conversions to and from decimal form. So we'll start with nice and easy. The idea is that we're taking a decimal form and we're putting into a fractional form A on B. And the whole process here is going to be getting rid of any patterns within the decimals. We'll start with terminating form. As we said, terminating decimals only have finite number of decimal places, so an easy example would be something like 1.21. Okay. The easy process here is that we find a way to set it up so that we can convert or multiply to remove any decimal places. So in every instance, the best way to start a question like this is to assign a variable to it. So we might say that x is equal to 1.21, or we can let x equal 1.21. Now, what do we have to do to x in order to make this an integer value? The idea should be, okay, we can see that we need to multiply by 100. So if we multiply x by 100 and we get 100x, then we get 121. We can now isolate x by dividing by 100, and we end up with x is 121 on 100. So it's as simple as that. If the fraction can be simplified now, we'll do that, but the idea is that we just go through a process to eliminate any decimal representation of numbers. So the easiest way to do that is multiply our left-hand equation, right-hand equation by some equivalent value. Look at another really quick example of that one. Let's make one up. We'll say 3.125. Now, we'll say let x equal 3.125. And we can, if we're having trouble recognizing that 0.125 as a common decimal that we should know, which is 1/8, we would say multiply by 1,000, and we get 1,000x, and that will give us 3.125. When we divide by 1,000 here, so x is 3.125 on 1,000, now we can go through some process of simplification. If we divide by 25 on top and bottom, then 25 goes into 1,000 40 times, so on 40 goes into 3,125 125 times, and then we can simplify that again, and we can again divide by 5, and we get 25 on 8. There it is, represented as a fraction in an improper form. Now, if we were smart here, we would have realized that all we need to do is multiply by 8. So we could have said that 8x is equal, now 3 times 8 is 24. 0.125 multiplied by 8 is 1. So we've got x is equal to 25 on 8. And we've got our solution much quicker. But that comes down to recognize some of these decimal representations of common fractions. Okay, so terminating, not so bad. We'll now look at reoccurring. Now the process for this is similar, but it takes a little bit more of a jump. Now the whole idea with reoccurring decimals is that we can work to try and remove that repeating pattern. So we have to find a way to get that repeating pattern in two different ways, so that we can use a difference or a subtraction to remove the recurring component. So that's going to be our approach. We'll break it down. We'll look at it as an example. So let's say we're looking at 1.3 reoccurring. Now we all know that 0.3 reoccurring is 1/3. So this is a nice easy example, an introduction to this. So the first step again is that we can let x equal 1.3 reoccurring. Now, what we need to think about is what can we do to x to get another example with that same decimal representation. So, if I say let's multiply by 10, then we get 10x is 13.3 reoccurring. Now, the secret here is that in both of these we've got 0.3 reoccurring. And if we determine the difference between these two, so let's say 10x subtract x, then we've got 13.3 reoccurring, subtract 1.3 reoccurring, and that means this component here cancels itself. So 0.3 reoccurring, take away 0.3 reoccurring, and then we only have to worry about this 13 take away 1. So we end up with 9x is equal to 12. X is equal to 12 on 9, and we can find an equivalent fraction there, and if we divide by 3 on top and bottom, and we end up with 4/3. Right, this is our process basically. We need two representations with the same reoccurring decimal. So one more quick example. Let's say that we're looking at 1.43 reoccurring. So we'll say that we'll let x equal 1.43 reoccurring. And in order to get that same decimal representation, we can't multiply it by 10 because then we'd have 14.34. That wouldn't work. So we'll have to go 100, multiply by 100, and we get 143.43 reoccurring. We can now find the difference between these two. So 100x take away x ends up giving us 143 subtract 1. You'll notice that I didn't put in the 0.3 reoccurring. It's because I didn't need to. That's going to cancel out as I do that subtraction. So we've got 99x is equal to 142, and therefore our fractional representation is 142 on 99. Okay, so nice and easy. So we'll go through a couple of examples here. So we've got 2 terminating. We've got, I'll cut that down to 3 reoccurring. We'll go through and we'll represent each of these in a fraction form. So 0.23, we can say that x is equal to 0.23, multiply by 100, and we get 100x is equal to 23, and therefore x is 23 on 100 when we divide both sides by 100. Here we can say that x is equal to 0.015. Now in this case we're going to have to multiply by 1,000 to get rid of those 3 decimal places. So 1,000x is 15. Divide by 1,000, we've got 15 on 1,000. Now if we can see a common factor of 5 there, we can divide by 5 on top and bottom. We end up with 3 on 200, and that's our 0.015 as a simplified fraction. For our 3 recurring scenarios, we start with 0.3 recurring. Now we already know this is going to be 1/3, but we'll let x equals 0.3 recurring. We know that 10x is 3.3 recurring, and therefore 10x take x will be 3.3 recurring, subtract 0.3 recurring. Recurring is unimportant there, and we end up with 9x is equal to 3. X is 3/9, and as a simplified fraction, it is 1/3. In our next one, we've got 2.35, where the 3/5 is recurring, so we can let x equal 2.35 recurring. 100x, so we want to bring the whole 3/5 in front, is 235.35 recurring. And when we look at 100x subtract x, we end up with 235 subtract 2. So 99x is 233, and therefore x is 233 on 99. Now last example is we've got 10.123. So we can let x equal 10.123. Oh, 123 is recurring. 1000x is 10.123.123 recurring, and therefore 1000x subtract x, cancel out the decimal component, and we've got 10.123 subtract 10. So 999x is 10113, and therefore x is 10113 on 999. Now I'm not too sure if I can simplify that fraction, so I'm just going to leave it in this form. All right, so that's our process. Now just really quickly, if I wanted to work backwards and I wanted to look at something like 2/9 as a decimal. Now if you know your common fractions, you know that that's 0.2 recurring because 1/9 is 0.1 recurring. If not, the process you'll have to go through is just basically performing that division. So we're looking at it as 2, and we're dividing it by 9. Now because we know this is going to go in the decimals, we need to include a few zeros. Remember, the goal is that we'll perform a couple of iterations here using short or long division, whichever you prefer, and we'll then be looking for a pattern in the decimals. And once we find that, we should be able to assume that it will continue that pattern. All right, 2 divided by 9, not possible, so we get our 0. Now, obviously, we've used none of that. We can say that there's 2 remaining and we bring down the 0. So now we're looking at 20. 20 divided by 9, we get 2, and that means we've used 18, and we've got 2 remaining. We can bring down the 0, and we can already see what our pattern's going to be. 20 divided by 9 is 2, subtract 18, we've got 2 remaining, and so on. So that tells us that we've got 0.2 reoccurring. So 2/9 is equal to 0.2 reoccurring. I'm not going to need you to do this in most scenarios. Generally, it should be that you know those decimal representations of common fractions. But if you need to, there's a process. You need to go through a long or short division process to be able to determine that decimal. Okay, so now we're on to our last focus, which is interval notation. Now, interval notation is basically just a simple way to demonstrate a range of values. So, for example, and really, interval notation is just one way that you can do this. There's lots of different ways that you can do this. Interval notation is going to be an important approach in both senior methods and specialists, because they'll use this notation in order to shorten the way they deliver questions and introduce information. So if I wanted to say the numbers 2 to 7, now as long as we're including 2 and 7, then we can do this a number of ways. We could draw it on a number line. Now on a number line, if we're being inclusive, so we're including the values and we use a coloured in circle, so if 2 and 7 are involved, then we use a coloured in circle and we go 2 to 7. We could also say that 2 is less than or equal to x is less than or equal to 7. So that means that we're looking for a value x that's between 2 and 7, and the equals here allows us to include 7. Or finally, and this is our interval notation, we can say that x is an element. So that's saying that our value x includes the values. Now this square bracket means inclusive, and we can say 2 through to 7. So square bracket means we're including 2 and we're including 7. So all these three things are the same. Now, if I slightly adjust what I've said here, and now I say numbers 2 to 7 not including 2 and 7, then the only thing that changes in this number line representation was still 2 to 7. We use an open circle. An open circle suggests that those values are not included. So it's between 2 and 7, but not including those values. When we write in the inequality form, we are saying that it's 2 less than x less than 7. So that means we're between 2 and 7. X is between 2 and 7, but doesn't include them. So that equals there stops it from being inclusive. And then finally, when we look at interval notation, we're saying that x is an element. And instead of using square brackets, we can use circle brackets. So circle brackets suggest that it is not included. All right. So if we scroll back up, we can see that this is saying that same thing. The only thing that's left out is the number line representation, and we'll look at a couple of examples that include that. But you can see here, when we look at A, B with the circle brackets, then we're looking at A through to B, not inclusive because we've got the less than signs that don't include the equals. So x is between A and B, but not including A and B. Here we've got A and B. We've got a square bracket on the upper limit. So x is between A and B, and the big difference here is less than or equal to. So that's saying that B is included. So B is inclusive, so we use the square bracket. When we're looking at A up to positive infinity, so we cannot be inclusive with infinity because infinity isn't a number. So if we're including infinity, the idea is that it must be non-inclusive. We have to use that circle bracket. So we can see here that's just saying that x is greater than A. So x is greater than A. You could also, if you wanted to, say that that could be A is less than x is less than positive infinity. That would achieve the same thing. So I'm hoping that you can see now that anything that is inclusive, that is equal as well, is a square bracket. Anything that's not inclusive is a circle bracket. And really that's the lesson here. This interval notation will be something that we use all the time, particularly when we're sketching things and we're defining functions, or we're just setting up a question that has a certain set of values we're going to consider. All right, so we'll look at a couple of examples and this will finish off the lesson. So we want to sketch on a number line this 2. So I should have written x is an element of 2 through to 5, where 5 is inclusive. So we can draw our number line here. X, the values that are important are 2 and 5. 2 is non-inclusive, so open circle. 5 is inclusive, so colored in circle. And we can join that up and we can say it's everything in between, including 5. We could also, if we wanted to, say that that's 2 is less than x is less than or equal to 5. So that's not necessary for this question, but it's still nice to write that down. Now here we want to write an interval notation, and we've got x such that x is greater than or equal to 3. So this tells us that our lower limit is 3 inclusive. It's including 3, and it's going up to positive infinity. So we could write this as 3 is less than or equal to x is less than positive infinity, or we could say that x is an element. Now this is interval notation. 3 is a lower limit, and the upper value is positive infinity. Okay, so hopefully that makes sense. That's just a conversion into interval notation. Now, final questions here. We just want to illustrate each of the following intervals of real numbers. So we want to sketch them on a number line. Let's just do A, C, and D. So for A, we've got a number line, and we'll say that's x. -2 is my lower limit, 3 is my upper limit. If we want to, we can put a 0 in here if that makes us feel better about ourselves. -2, -3, both are colored in because we're inclusive of those values. And there we have it. When we look at C, we're -infinity down to 2. Now the problem is on a number line, how on earth do I represent -infinity? Now the reality is we're not going to do that. We'll say this is 0 and this is 2. 2 is inclusive, so it's a square, so it's a colored in circle. We can't go all the way down to -infinity, and it would be silly to try. So if I draw that line, and at the end of it, I put a arrow on, that's going to tell us it's going to continue down. If you really want to, you can put a -infinity, saying that it's approaching -infinity. That's not necessary. And there we have our number line representation. Our last one, we're saying it's from -3, so we can put our number line again. We've got -3, we've got 0 here. It's not inclusive, so it's an open circle, and that's just going to go off to positive infinity. And that looks like I wrote something weird, so positive infinity. Okay, so hopefully this all makes sense. A little bit of a practice with conversions with decimals and fractions, but also an introduction to interval notation. The questions that you will be doing are pretty simple representations of this same skill. So you'll be looking at questions 3, 4, 5, and 6. All right, thank you.